Hey guys, so in today's lecture, we are going to discuss design considerations of wind turbine. So, what do you mean by design considerations? So, design considerations means before designing a wind turbine, what kind of parameters we need to know or we need to find such that we can design the wind turbine, so that it can be helped by giving the dimensions of the wind turbine to the manufacturer. So we need to fix the dimensions. So based on what factors we will fix the dimensions, that we are going to study. So as we know that a wind turbine converts varying power into wind into useful form as electricity. So the productivity of the turbine is a function of both turbine design and wind resource. So productivity of the turbine is the function of both, that is, first is design, it is turbine design which we are going to do, and wind resource, that how much wind we will is available to us. So however, one cannot control our wind resource, so we cannot control this, but we can control this. So basically it should produce power at very low cost. So objective is to produce power at low cost. So therefore the fundamental design goal is to keep the cost of the power lower from the turbine of the available design. So the wind turbine may be exposed to severe and unpredictable environmental conditions, due to which rotor design becomes very complicated. The general procedure which we are going to start is identification of rotor parameters. Rotor parameters. So the choice of an aerofoil, then an initial blade shape is found using optimum blade shape assuming wake rotation. The final blade shape and performance are obtained iteratively based on drag, tip losses, and ease of manufacture. So we will find the parameters. So first we will find the diameter of the rotor. So rotor parameter, we are interested in finding diameter of the rotor. So as we know that power P, so we'll see power P is equal to uh, CP CP into efficiency eta into uh, what is the power P, that is the kinetic energy of the wind, that is 1 half mv square. So 1 half mv square can be written as pi by 8 rho d square vi cube. So from where this pi by 8 came, so that is 1 half m dot vi square. So from this we can write that 1 half mass, we can write rho into area A into vi velocity, and vi square is there. So we will get 1 by 2 rho A is area is pi by 4 d square, so vi cube. So we got finally pi by 8 rho d square vi cube. So this equation we have used here for power So it is pi by 8 root d square vi cube. Now we are interested in finding the diameter d. So we'll make diameter d as a subject. So diameter d will be equal to 8p divided by cp eta rho pi vi cube raised to 1 by 2. So this is the diameter of the rotor. So now we will find the maximum torque, that is T maximum, on a turbine rotor, which would occur when maximum thrust can be applied. Thrust means that is force is applied. So as you know, torque is force into distance. So maximum thrust F maximum into radius, that is d by 2, which will be equal to, so which is equal to F maximum into R. So what is F maximum? So F maximum, that is force, so that is 1 of mv square, so that is 1 by rho 1 by 2 rho a vi square into R. So this is torque T maximum that can be applied. So now for a wind turbine producing a shaft torque T, the torque coefficient Ct can be defined as, that is T is equal to Ct into T max, that is maximum torque into Ct. Now we will define a new term, that is tip speed ratio. This tip speed ratio. So tip speed ratio lambda is defined as the ratio of the blade's outer tip speed, so that is V outer tip speed divided by to the upstream wind speed, so V upstream or free wind speed, so that is lambda is equal to Vt by Vi, so which is equal to omega r upon Vi. So this is the tip speed ratio, that is lambda is equal to omega r by Vi. So where omega is angular velocity, r is outer blade radius, so substituting the value of this r in the equation, we will get, so we will substitute, so let's make r as a subject first. So lambda into Vi upon omega is equal to r. Now we will use this r in Tmax equation. So Tmax is equal to 1 by 2 rho a Vi square into r. So we'll put r here. So uh, r will be lambda into Vi upon omega. So this will become 1 by 2 rho a Vi cube into lambda by omega. Just wait a second. So Vi cube lambda by omega. So this is the maximum torque value. So as we know that 1 by 2 rho a Vi cube is power Pt. So T max is equal to Pt upon lambda by omega. So we got that T max is equal to Pt by lambda by omega. So T max is equal to Pt into lambda by omega. So the shaft power P is equal to, as we know that, T into omega. So P, which is also equal to Ct into T max into omega. So substituting the equation, that is P is equal to Cp into Pt. So P is equal to Cp into Pt. So Pt is theoretical power, P is real power, and Cp is coefficient of power, that is Cp. So we will find the relation between them. So we will find the relation between them. So on the one side we have Cp into Pt. On the other side we will compare this both equation. On the other side we have Ct into T max. So we will use the equation of T max this. So that is Pt into lambda by omega into, then we have omega. So omega cancel, Pt cancel. So we got the relation Cp is equal to Ct into lambda. So coefficient of power is equal to coefficient of torque into lambda. So in practice, power coefficient and torque coefficient are both function of lambda and are not constants. So this says that this C, P and Ct are not constants. So they are functions of lambda. So these are functions of lambda. So from Betz criterion, so from Betz criterion, so maximum value of Cp. So Cp maximum is 0.593. So in ideal case, Ct maximum will be 0.593 upon lambda. So the tip speed ratio is chosen according to the application. So it is chosen according to the application. So now if we plot a graph, suppose say, oh sorry, of tip speed ratio versus number of blades. So number of blades tip speed ratio versus number of blade. So suppose tip speed ratio is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And suppose number of blades are 2, 2, 4, sorry, 2, 4, 6, 8, 10, 12. So the graph of number of blades versus tip speed ratio will be this. So water pumping wind turbine requires higher torque, for which lower value of lambda in the range, that is 1 to 3 is used. So when wind generators where lambda range should be higher, that 4 to 10 is used. So so the optimum power extraction, that is tip speed ratio at optimum power extraction, is given by that lambda is equal to 4 pi upon number of blades. 4 pi upon number of blades. So this is the relation between tip speed ratio and number of blades. So now we will see another term, that is solidity. It's SOLIDITY. Solidity its symbol is sigma. So what is solidity? So it is the ratio of the blade area. So blade area to the swept frontal area to the swept frontal area of the wind turbine. So it is the ratio of two areas, that is blade area upon swept frontal area of the wind turbine. So solidity determines the quantity of the blade material required to intercept a certain wind area. So how much quantity is required to intercept a certain wind area? So that we can find from this term, that is solidity. So solidity sigma is equal to B R B upon pi r square. So swept frontal area is pi r square and blade area is BRB. So what is B? So B is number of blades. Then what is B? This is blade width. Blade width, and this R is blade radius. R is blade radius. So sigma will be equal to BB upon pi r. So r get cancelled. So sigma will be equal to BB upon pi r. So a 2 or 3 bladed wind turbine has low solidity and so needs to rotate faster to intercept and capture wind area. So if we plot a graph of solidity versus tip speed ratio, then So suppose tip speed ratio versus solidity. So we'll get a graph in such a manner. So so this is 1 2 3 to 8, and suppose this is 0 0.1 to 0 0.6. So we will get a graph in such a manner. So as here we can see that as tip speed ratio is increasing, so the solidity is reducing. So in similar manner, if tip speed ratio is reducing, the solidity is increasing. So if 2 to 3 blade rotor are there, then the solidity is very low. So if more rotors are there, then solidity will increase. So this is the graph of tip speed ratio versus solidity. So these are the main these are the main uh, characteristics of wind turbine. So we will see performance characteristics also, performance uh, of wind turbine, how it can be calculated in the next lecture. So thank you very much.